Let F denote a field, and let A be an n by n matrix with entries in F. We call that the null space of A, denoted by n of A, is a set of x in Fn such that Ax is equal to 0. Notice that every element in this vector space comes from Fn. In fact, Fn, which is the set of all n tuples with entries in F, form a vector space as well, where the scalars are from the field F. And this is probably the most common vector space studied, especially when F is the set of real numbers and n is less than or equal to 3. For example, R2 is usually depicted by a two-dimensional plane and R3 by a three-dimensional space. Now, because n of A is a subset of Fn, and both of these are vector spaces, we call n of A a subspace of Fn. And we're going to define the notion of a subspace formally very soon. But before we do that, let's look at another example of a very common vector space, and it's given by the set of all m by n matrices with entries in F, and scalars are from the field F as well. The zero vector in this vector space is the matrix of all zeros. And another example of a vector space is the set of polynomials in X with coefficients from the field F, where polynomial addition is the vector addition, and multiplying a polynomial by a scalar gives you the scalar multiplication. And the zero vector is the polynomial that is identically 0. The polynomials could be degree restricted. You can talk about the vector space of all polynomials in X, or you can talk about the vector space of polynomials in X with degree at most k. So the quadratics are polynomials with degree at most 2. And every vector is in this form. So what is a subspace? Suppose that V and W are vector spaces such that the set of vectors in W is a subset of vectors in V. And V and W have the same vector addition and scalar multiplication. Then W is called a subspace of V. Furthermore, if W is not equal to V, W is said to be a proper subspace of V. So in the case of a null space, unless the matrix has all entries equal to 0, the null space is always a proper subspace. A question that comes up very often is the following. Suppose you are given a set W, and every element of this set is a vector of some vector space V. How do you tell if W is a subspace of V? Well, of course, one can check W against all the properties of a vector space. But it turns out that there are only two things that you need to check. You need to check that this set W is closed under the vector addition and scalar multiplication for V. So for example, say W is the set of two tuples AB such that A and B are integers. So clearly W is a subset of R2 because every two tuple here is an element of R2. Now notice that W is closed under addition because if you take any two tuples A, B, and C, D, where A, B, C, D are integers, you get A plus C in the first entry and B plus D in the second entry. And now both of these are also integers. So this is in W as well. But is W closed under scalar multiplication? Well, the answer is no. Because if you pick, say, this element from W, take half to be a scalar, half of 1, 0 is 1/2 0, and that is not an element of W. So W is not closed under scalar multiplication, and so W is not a subspace of R2. And now let's revisit the null space of A. We already know that n of A is a vector space, but we're going to pretend that we didn't know that. And all we know is that n of A is a subset of Fn. Now to show that this is a subspace, we just need to show that n of A is closed under addition and scalar multiplication. So if you take any xy in n of A, the question is x plus y in n of A? And to check that, we just need to take A times x plus y and that can be written as ax plus ay, and that's 0 plus 0 equals 0. So x plus y is also in n of a, and so n of a is closed under addition. What about scalar multiplication? So take a scalar from f and an element from n of a. Then the question is alpha times x in n of a? And to check that, we need to take a times alpha times x, and that can be written as alpha times a times x, and that can be rewritten as alpha times a times x, and that's just alpha times 0, and that's just 0. So alpha times x is also in the set n of a. And that shows that n of a is closed under scalar multiplication as well. And we conclude that n of a is a subspace of Fn.